Hello and welcome to the first day of chapter 9. Today we are talking about a new thing. It's called significance tests. So in a significance test, what we're trying to do is actually make a decision about something. So we're going to test like hypotheses about claims that we're going to make and then make a decision with it to see whether our hypotheses were correct or not. So for a significance test, we define this as a formal procedure to test two claims or hypotheses. So we're actually making like two hypotheses. That way they contradict each other, and so we can either prove one of them right and the other one wrong, or the other one right and the first one wrong. Something like that. But we have a formal procedure for this because we want to make sure that when we do this procedure to test our hypotheses or our claims, that we do all our math, check everything that we need to make sure that we can actually calculate probabilities, things like that, because we are using probabilities in order to prove our hypotheses. So the general steps for a significance test. First thing is to actually write out the claims or the hypotheses. So there's two. The null hypothesis and the alternative hypothesis is what we call them. The symbols that we use for them look like this. For the null hypothesis, we have this symbol here. It's in capital H, like for hypothesis, and then like a little O for a subscript. So it's actually read as H naught, but we'll just call it HO. So this is usually a statement of no difference. It's basically, we're saying it always equals whatever we're talking about in the problem. So in the HO, you always use an equal sign. There's no other option. But then the alternative hypothesis, we use the symbol HA, so A for alternative. This is the claim that we're actually trying to find evidence for. So in your problem, it should tell you this is what we're claiming, and so that's what you would put in your HA. And depending on what the claim is, that's how you're going to know when to use the greater than symbol, the less than symbol, or the not equal to symbol. And depending on whether your alternative hypothesis is the symbol that you use in your alternative hypothesis, that determines whether you have a one-sided test or a two-sided test. So this is an important distinction to make because when we eventually calculate probabilities, that's when you need to know whether it's one-sided or two-sided. So the way to tell is you always look at your HA. So look at your alternative hypothesis. If your symbols that you're using are either a less than symbol or a greater than symbol, then it's considered one-sided. So if you think about your normal curve and finding probabilities on a normal curve, if we only shaded one side of it, either the right or the left, that would be because you're either doing a less than or greater than problem. So that's why it's one-sided. Two-sided is whenever you use the not equal to sign. So it doesn't specify whether you want less than or greater than, so it counts as both. So two-sided. So let's do a couple examples to actually write out the hypotheses for a claim. For example, on its website for the 2020 census, the U.S. Census Bureau estimates that completing the census questionnaire will take 10 minutes on average. We suspect that the time it takes to complete the form may be longer than advertised. State the hypotheses. So we know we have to write an HO and an HA. So remember, HO is our statement of no difference. So in this question, we talk about something about 10 minutes on average. So that's kind of the number that we're, claiming. And then we suspect that the time it takes to complete the form may be longer than advertised. So 10 minutes, or we think that it's more. So the claim here is going to be that it's going to be longer because that's what we're suspecting. So that's our claim. And longer usually means greater than. So that's how we will know to use in our HA. We're going to use the greater than symbol. The number we're going to talk about is the 10 because that's the number we're making a claim on. In the HO, then because we always have to use an equal sign, it'll be equal to 10. And because we're talking about averages here, the symbol we're going to use for averages is mu. So our full hypotheses are going to look like this. HO, we're going to use the little colon to tell people what the null hypothesis is. The mean, the true mean, is the mu symbol, is equal to 10. So 10 minutes on average is what we're saying in the problem. Our alternative hypothesis, our actual claim that we're trying to find evidence for, is that the true mean is greater than 10. Or that we're taking longer than 10 minutes to complete the census questionnaire. So that's how the format of an alternative hypothesis look every single time. The things that's going to change are the numbers, because it'll depend on what it says in the problem. The symbols is always going to be equals for HO, And then for the HA, again, depending on the problem, that's how you know to use whether the less than, greater than, or not equal to symbol. And then the mu will change. If you're not talking about averages, then it'll change. So like this next problem, we're talking about the National Sleep Foundation. 85% of teens are getting too little sleep on school nights, according to the National Sleep Foundation. Jamila wonders whether this result is true at her large high school. She asks a simple random sample of 100 students at the school how much sleep they get on a typical school night. In all, 75 of the students reported getting less than the recommended amount of sleep. State the hypotheses. So in this case, we're not talking about averages here. They give us a percentage. The other number that we have is talking about like how many students are in their sample size, which isn't something we're trying to make a hypothesis on. We don't need to hypothesize whether we have 75 students or not. So the really number that we need is the 85%. So to set up our hypotheses here, the HO, the HA, because we're dealing with the 85%, that's the number we're going to use. So kind of like the other problem that we did, instead of 10, it'll be 85%. But of course, percentages, we always turn them into decimals, so this will be 0.85. So our HO is going to have equals 0.85, but we no longer have averages here. Percentages is called a proportion, so we're going to use a different symbol than mu. This would be, to stand for proportions, we use the letter P. So there's my null hypothesis. For my alternative hypothesis, remember this depends on what the claim says. So in this problem, we have the 85%, but then after we did our simple random sample and the survey about how much sleep they get on a typical school night, it says the students are reporting less than the recommended amount of sleep. So here, less than, now we know to use the less than symbol. So P is going to be less than 0.85. So in general, the number that you use is always going to be the same number for both the alternative hypothesis and the null hypothesis. Just it's the symbols that change, the equals or the less than. So the next step that we want to take in a significance test is called the p-value. So the p-value, the p in p-value stands for a probability. We're just calculating a probability here. But because we're using this probability to prove our claim, that's why we have a special name for it, the p-value. So by definition, the p-value is when you assume that your null hypothesis is true. So remember, our null hypothesis is the one that it's equal to. So assuming that's true, we're going to find the probability using a normal curve. So we're trying to find the probability for getting in our sample, whatever our observed evidence is, as strong or stronger. So we're basically looking at like a normal curve and seeing whether the probabilities towards the ends, because that's where it's strong or stronger than the middle part of it, which is what our null hypothesis is. So we want that probability, it counts as like getting evidence for your alternative hypothesis. So we're basically using this probability to prove our alternative hypothesis. And so the p-value that we get, the probability that we get, we want this number to be really small, because what that means is if you get a really small number, that means a probability that's really small means it's like very rare to happen. And so if what we're assuming is true and we got something that's supposed to be very rare, but in our sample we actually got it, that means it doesn't make sense for our null hypothesis to be true, because that's what we were assuming to begin with. So it's basically saying we're assuming wrong, and so we got this really low probability. So when you assume wrong, then that means the null hypothesis can't be true. So that's how we're kind of proving our hypothesis. If we can prove the null hypothesis, the HO, to be wrong, then we know that HA, where our claim actually is correct. That's what we use the p-value for. So how do we determine whether our p-value is small or not? That's when we use our p-value to compare it to this thing called the significance level. We use the Greek letter alpha. I know it just looks like an A, but like a little bit more like curly. This is alpha. The significance level alpha is used to determine like how strong our evidence is. Because the smaller number alpha is, then it proves that our p-value is even smaller than that, and so it gives us very strong evidence against the null hypothesis. The numbers that we use for alpha are usually 0.10, 0.05, or 0.01. So the smaller number you use for alpha, the larger your strength of your evidence. So it's actually better to use smaller numbers, but the problem itself will tell you what number to use. So we're looking at our p-value that we calculate, and then we're going to compare it to whatever number they tell us in the problem. So if the p-value is even smaller than alpha, then that shows that the null hypothesis is wrong. And so we call that rejecting the null hypothesis, and that's a conclusion that we can make. So if the p-value is smaller than alpha, then we reject HO. That means we do have convincing evidence that our alternative hypothesis, HA, is true. But then the opposite is also a conclusion that we can make. If your p-value is greater than alpha, that's when we fail to reject HO. So if you fail to reject something, you're not rejecting it. We do not have convincing evidence that HA is true. Because remember, if you reject HO, that means HO is wrong, so HA is true. If you fail to reject HO, then we don't think that the HA is true because we weren't able to reject HO. One thing that we never do is that we're never going to accept our HO, because you either like reject, the opposite kind of sounds like you would accept it, but that's not something that we're proving. We're always trying to prove whether HA is true or false. That's our claim. So we're not proving anything about HO, because our HO, all it says is that it's like equal to some number. Well, just because our HO is that it's equal doesn't necessarily mean that's true either. Because if we're trying to prove whether, like for this example here, that our average was greater than 10, if we disprove that and say that HA is wrong, it's not necessarily that it's just equal to 10. It might be less than. We don't actually know. So we never accept our HO. We just prove whether HA is true or not. So let's do a full example. In this problem, a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a simple random sample of 15 new deluxe batteries and uses them continuously until they are completely drained. The sample mean lifetime is 33.9 hours. The resulting p-value is 0.0729. What conclusion would you make at the alpha equals 0.01 level? So first, let's start with our first step, our hypotheses. So we're writing our HO and our HA. So looking back at this problem, we know we're talking about an average of some sort. 30 hours is the number that we're probably looking at because that's the average that they're talking about. So if we're using an average, that means the symbol we're going to use is mu. And then the company also would like to be convinced that they really do last longer. So that's what we're trying to see, whether it's going to be like longer than 30 hours. So my HO and my HA, I know I'm going to use mu, 30 as my number, and then longer would be greater than for the HA. All right, so we've got our hypotheses. Next, we're going to compare the p-value with alpha. So they told us the p-value, they already calculated it for us, was 0.0729. And we're using the alpha level, the significance level of 0.01. So we're trying to prove that, like, give really good evidence because it's a really small alpha level. So our p-value here, 0.07, is definitely greater than 0.01. So if the p-value is greater, that's when we fail to reject. So our final conclusion, we are failing to reject HO. That means that we don't have convincing evidence that the HA is true. So we would, since our HA is talking about being greater than 30, we do not have convincing evidence that the deluxe battery lasts longer than the regular battery. So that's the decision we were able to make from our significance test here. So the last part of these notes, we have a couple errors that we could be making. Basically, because we're making decisions based on the significance tests, if we either reject HO or fail to reject HO, what if we make a mistake? What if our probability that we find is not good? What if the sample that we got in our problem was not good? What What if there's bias? Whatever. So when we make errors, there's two types, and it's very originally named, type 1 error or type 2 error. So this is based on whether you reject or fail to reject HO. So in a type 1 error, we mistakenly reject HO. So we reject HO as our decision, as our conclusion, but this was wrong. So if we reject HO, that means we think HA is true, but in reality, HA is not true. Type 2 error is the opposite. If we mistakenly fail to reject HO, we think that HA is false then. However, that's our mistake. HA is actually true. So, using the last example, we're going to describe the results of a type 1 error and a type 2 error, because sometimes one is worse than the other. In this last example, we're talking about our AAA batteries, the deluxe versus the regular, and we think the deluxe battery is supposed to last longer than its advertised 30 hours. So we ended up failing to reject HO. So like potentially we could have made a type 2 error, because that's the one where you mistakenly fail to reject HO. But if we had made a type 1 error, this is what it would sound like. We would think that the deluxe batteries last longer than the 30 hours, but they actually don't. Type 2 then would be the opposite. We think the deluxe batteries don't last longer, but they actually do. So consequences of this would be, for type 1, if we think the deluxe batteries last longer than 30 hours, then we probably make more of them, because then we can sell them for more and it's good look. But if they don't actually last longer, then we are spending more money to make these deluxe batteries, but they're not going to sell as well because they don't actually do anything, because they're the same as the regulars. So then with a type 2 error, even though we think that the deluxe batteries don't last longer, when they actually do, then the company, we don't waste any money making more deluxe batteries because we don't think that they last longer. So we're basically potentially losing out on sales here. So to determine which is worse, if we were the company, type 1 error probably would be worse because you end up wasting money and you don't get the sales of the deluxe batteries, versus type 2, you're like losing out on potential sales, so you haven't like fully lost out, but like, because now you're just making regular batteries and selling regular batteries. You're not losing anything, just potential sales. So type 1 error in this case would probably be worse. Although if you were looking at it from a customer perspective, then you would end up, for type 1 error, you would end up buying deluxe batteries and like spending more, even though they don't actually work. So depending on the perspective that you're looking at, I think in this case we want the company's perspective because that's who's making the claim and everything in this problem. But that's why a type 1 error and a type 2 error really depends on how the question is being asked. So that's something we want to think about. And that's it for our significance test for today. Thanks for watching. Don't forget to like and subscribe. Bye.